Okay. So I'm a PhD student at the Cyprus Institute, and today my presentation will be mostly an overview of our work in our research group there in Cyprus. And the title of my presentation is Advancing Biometeorological Insights from Temperature Extremes, Thermal Indices, and Compound Stressors on Health in the Mediterranean. So, what is the problem? As we're all aware, climate change is a global challenge, but mainly in the Mediterranean area because the warming there is nearly double the global rate. So what does this mean? The frequency, the intensity, and also the duration of these extreme events are increasing rapidly. So why this is a big problem? So extreme events can pose significant risks to public health by exacerbating bioclimatic stress, and these events can lead to increased mortality and hospitalization. Now, regarding this mortality and hospitalization data, we have identified some research gaps. First of all, there is substantial scarcity of systematically collected and accessible health data across the Middle East and North Africa region. And despite the fact that there are some existing datasets, these datasets are fragmented, they're not standardized, and often they're lack in longitudinal continuity. So we could find some data, but the access remains restricted. And even in Europe, where the health information systems is comparatively advanced, again, we are facing some problems. Finally, Eurostat can serve as a primary mortality data, but it only provides all-cause mortality with limited temporal resolution, and that means it is only reported by weeks, sorry. So finally, in many cases, the more granular data can only be obtained through individual governmental agencies, and accessibility is inconsistent. And as far as you can understand, is a bit a problem if you want to study the relationship between heat and health. So what is our approach? Because the relationship between the temperature extremes and health outcome is very complex and non-linear, we are trying to develop statistical models in order to capture these patterns effectively while ensuring robust and interpretable results. So here's an overview of our statistical model. We are using the distributed log nonlinear models, and we implemented this as penalized generalized additive model. So these DLM models are an extension, these DLNMs are an extension of the DLMs by incorporating nonlinear relationships. Also, these models can capture the relationship between stressors, let's say temperature, UTCI, or other matrices, and health outcomes over time. They can easily capture the distributed impacts across lags. It means you're going days back of the event, enhancing flexibility and understanding of how these stressors are affecting health outcomes over time periods. And note here that the use of the DLNMs is a primary tool in epidemiological studies. So more information about our model. The generalized additive models are non-linear relationships without subjective biases. So this means that we avoid the need to select an optimal polynomial degree. So GAMs, they're using smooth functions for a robust and flexible modeling approach. And with that, we avoid the range phenomenon, as you can see here. Also, these predictive simulations, they prevent the overfit, as you can see over here, and they are ensuring that our model captures the patterns while remaining robust to noise and outliers. Also, this method enables for model checking, so to see if our statistical model is working properly. Now, the application of our model. First of all, here, as you can see, there is a paper recently published by our supervisor, TZYRKALLI, and basically it's a tutorial on the flexible distributed lag models for count data using R and the package MGCV. And by using this methodology, in our group, we had plenty of publications. So first of all, here we have a recent publication from our co-author Francesco Schecco, which is about temperature extremes in human health. So they investigate the interaction between heat waves and mortality. Second, here you can see another study from Jan Naros. Again, it's a very recent publication, which is about the combination of the MPET, and the mortality data for an application for Athens in Greece, and also a synergistic impact of air quality and thermal conditions on mortality for Thessaloniki by Barliari and al. So, let's see some results regarding the temperature extreme. So in this study, the research focused in investigating the mortality profile risks between two seasons for distinguish between typical and heat wave days for Cyprus. So the data that we use for this study is daily mortality data regarding cardiovascular and respiratory diseases from 2004 to 2019. For the whole island of Cyprus. Here, as you can see, is the results for the warm period, and on the other hand, for the cold period. The upper plots are referring to the typical days for warm and cold, and as well, the below panel is referring to the heat wave days. So if we focus in this plot, which is a two-dimensional relative risk plot, with the red we can identify the higher risk, higher mortality risk, with blue, lower mortality risk, and the dashed dots, they represent the statistical significance of our model. So as you can see here, we can see that for typical days, the elevated mortality risk is identified at very high temperatures. As you can see, they're spanning from 30 to 40 degrees, peaking at shorter legs, let's say up to 4 days. But if we're going to the heat wave days, we can see that further increase of the mortality risk during heat wave is pronounced over here. On the other hand, here we can see that mortality risk at it appears at very low temperature during cold season and for longer days. So more details about the results. Here they calculate the attributable fraction. What does it mean? This is the number that quantifies the proportion of deaths, or let's say the hospitalizations, directly to non-optimal temperatures, helping to assess the health burden of extreme temperature events. So here in the table, we can see that for the warm period, they calculate for typical days and heat wave days. And on the other hand, we can see the cold typical and cold wave days. Here is important to say that the cold wave days, as we can see here, they're linked up to 50% of total deaths in absolute numbers due to cardiovascular and respiratory issues, and significantly higher than the 19% here of the heat wave days. But however, if we compare now the rate of change of the typical days versus the heat wave days, the wave days, we can see that the attributable fraction is 5 times higher on heat wave days and almost 2 times higher on cold wave days compared to typical days. I forgot to mention here that this study is referring as well for the hospitalization, so it includes more details for the hospitalization results as well. So the main outcome from this study is we can say that for both high and low temperature, they pose significant public health risk, and especially in Cyprus, which is expected to be affected only by high temperatures because the climate there is it's having warm, very warm summers and very dry winters, sorry. So moving on, here there is a work that is under review. So here we wanted to directly quantify the synergistic effect of temperature and moisture on human mortality. So here we are using the same daily mortality data from 2004 to 2019 for the warm period, which expands from April to October for Cyprus as well. So here what we've done, we split our data into locations. So here on the left, you can see the coastal cities, and on the right, you can see the non-coastal cities. So regarding the coastal cities, each grid here represents the amount of water vapor pressure, so in different levels. And we wanted to see how temperature in conjunction with the water vapor pressure are interacting. So here in the coastal risk, in the coastal cities, we can see that there's higher, as we go up to the water vapor pressure levels, we can see that the combination with extreme temperatures, as you can see, more than 30 degrees, we can see that we have higher mortality risk. So the combination of high water vapor pressure and high temperature at shorter lags, let's say up to 5 days, so hot and humid waves are will significantly increase the mortality risk in Cyprus. So in the other hand, for low temperatures and as well low water vapor pressure for longer lags, let's say here from 5 to 10 days, we can see an elevated mortality risk. On the other hand, for the non-coastal, which is the capital of Cyprus, Nicosia, is the only inland city, we can see that increased mortality risk occurs during hot conditions at hot and short lags, more than 35. And as you can see, when we have low water vapor pressure, this is a case mainly, we have elevated mortality risk. So to conclude, we can say that our statistical model is applicable across multiple geographical contexts, depending on data availability, of course. So we can implement this in simple form with single stressor, let's say only with temperature, or we can incorporate this with multiple stressors synergistically, let's say temperature, vapor pressure, some other works with the MPED or air quality data by using a hierarchical framework. And what is next, basically, is to expand our model application in Europe, utilizing open source datasets from Eurostat to see if it's working there as well. So with that, I would like to thank you. And this is a bibliography. Thank you so much.